Okay, hello everyone. So since we had Hurricane Dorian kind of disrupted our plans, I wanted to do a quick video covering the activity that we were going to do on Tuesday. And so this is going to walk you through the solutions to the Week 3 Tuesday daily activity. Okay, so problem 1 says in 2019 the cost of sending a letter by the United States Postal Service is 55 cents for up to 1 ounce, plus 15 cents for each additional ounce. The problem asks us to finish graphing the cost for the cost function for the letters for weighing between 0 and 10 ounces. Okay, so here's the first few. Here are the first few pieces of this piecewise function. So it's defined to be 55 cents for 0 to 1 ounces, and then anything over 1 ounces it jumps up to 70 cents because that's 55 plus 15 more cents, 70 cents. Then between every integer after that, it goes up by another 15 cents. So 2 to 3 it's now 85 cents, 3 to 4 ounces it's now 100 cents, and so on. So we need to continue this pattern. So I'm going to plot these. So between 6 and 7 I need to go up from $1.30 to $1.45, which would be right there. And then from 7 to 8 I need to go up another 15 cents, so that should be $1.60. And then from 8 to 9 that would be $1.75. And then from 9 to 10, it should be $1.90. Okay, so that's the graph of the cost function. And the follow-up question is, how much does it cost to ship a letter that weighs 7.5 ounces? So if you look at the weight in ounces, you go over here, you say, okay, 7.5, that's between 7 and 8, that's going to cost $1.60. Okay, so that's just an example of something you'd see a lot in business where you have a piecewise defined function where the cost goes up incrementally based on weight. Okay, so problem 2 through 4 are all examples of finding limits algebraically or via substitution. So the first thing is the limit as x goes to 4 of x plus 4. And last week I spent a lot of time asking you to really internalize what the definition of a polynomial is. And so you should be able to look at that and say, yes, that's a polynomial because it's just a sum of powers of x with real valued coefficients. So it's x to the 1 plus 4x to the 0. So since that's a polynomial, it's continuous, and you can just plug in x equals 4 into that to get the limit. So that's going to be 4 plus 4 or 8. Okay, so anytime you see a polynomial and you're asked to find a limit, you can just plug in the value that you're asked to evaluate at, and that will give you the actual value of the limit. Now, this is a rational function, and the only time that rational functions blow up are when the denominator is equal to 0. And you can see that if you try to do substitution, if you try to plug in x equals 4 in here, you get 4 squared minus 16 over 4 minus 4, which is 16 minus 16 is 0 over 0. Okay, and so you might be tempted to say, well, I don't know, it's undefined or something, right? But what this means is that we can actually, we need to do some cancellation to get rid of the x minus 4 on the bottom. That means that x minus 4 is a 0 of the denominator and of the numerator, which tells us that if we factored this on top and bottom, we'd get something that would cancel. So this is equal to the limit as x goes to 4 of x minus 4 over x minus 4 times, and if you factor x squared minus 16, you should be able to do this in your head, but if you can't, I have a video on how to do polynomial long division in the college algebra series, and I'll put a link to that just so you get used to doing long division, or you can just learn to factor these things in your head. So this is x minus 4 over x minus 4. And now the key here is that the limit is not asking for the value at x equals 4, it's asking for the values as you get closer and closer to 4. And so as long as you're not actually at x equals 4, x minus 4 over x minus 4 is going to be non-zero, and so you're going to get some non-zero thing divided by some non-zero thing that's the exact same thing, so those will cancel and be 1. So this is equal to the limit as x goes to 4 of x plus 4, and we've already figured that out, that that's supposed to be 8. Okay, so in all these problems, if you get 0 over 0, that means that you should do some factoring and canceling. Okay, so here's another example. Find the limits and explain how they are related. The limit as x goes to 0 of 3x minus 1. Again, you should look at that and say that's a polynomial, and so I can just plug in 0 and I'll get negative 1. Now here, if you try to plug in 0, you're going to get 0 over 0, which means that you can factor out an x minus 0 out of top and bottom. So this is going to be equal to the limit as x goes to 0 of 3x minus 1 times x over x. And as long as x isn't 0, x over x will be 1. And since we're asking for the values close to x equals 0, not actually at x equals 0, we can cancel that. So this is equal to the limit as x goes to 0 of 3x minus 1, which we already figured out is negative 1. Okay. And notice that I'm writing down the terminology, the limit as x goes to 0, several times because I'm writing a statement that says that this is equal to this is equal to that. And if at some point, if I drop the limit sign before I've actually evaluated by substituting, then I would be writing something that's probably false because I dropped off an important part of the sentence. It's kind of like if you were to say the cat ran up the tree and then wrote equals cat. Like you just dropped a whole part of the sentence. It won't make sense. Okay, so let's continue with these examples. Here we have the limit as x goes to 2 of the polynomial 7, the constant polynomial 7, right? And so what is that going to be? Well, y equals 7 is just a constant line. That's going to be 7. So since x never showed up, the answer is always just 7 there. If you try to plug in 7 over here, again you'll get, if you plug in 2 over here, you're going to get 14 minus 14 is 0 over 2 minus 2 is 0. So again, we're in the 0 over 0 case. That means that x minus 2 must be a factor of the top and bottom. So again, I'm going to write limit as x goes to 2 of x minus 2 over x minus 2. And then if I factored out the 7 here, I'll leave that part there. Okay, so I factor the numerator, and you can see that if I were to distribute 7 back in, I'd get 7x minus 14. So that's just checking to make sure I factored correctly. And so now again, as long as x doesn't actually equal 2, x minus 2 over x minus 2 will equal 1. So then we get limit as we get the limit as x goes to 2 of 7 times 1, which is 7. Okay, problem 5 is of the same flavor, except for now we're going to be having to factor the denominator. But again, if you plug in x equals 2, you get 0 over 0, so that tells you that x minus 2 must be a factor of the top and bottom. So I write down the limit as x goes to 2, and now I need to factor the bottom. Well, the bottom is x minus 2 times x plus 2, and the top is 2 minus x, which I'm going to write as negative 1 times x minus 2, just because it's clearer than how I'd cancel. Okay, so again, you should check that if you distribute negative 1 in there, you will get negative x plus 2, which is the same as 2 minus x. But when I've written it this way, it's much easier to see that this is the limit as x goes to 2 of negative 1 over x plus 2. And now that's a rational function, but it's a rational function where I'm plugging in something that's not going to make the denominator equal to 0, so that's fine. I can just substitute that in, and I should get that the limit as x goes to 2 of negative 1 over x plus 2 is negative 1/4. Okay, now I just wanted to plot y equals 2 minus x over x squared minus 4, so you can see that the limit actually is negative 1/4. And so if I zoom out, this is what the function looks like in general, the graph of the function looks like in general. And now I want to zoom in on what happens when we get close to x equals 2. And you can see that if I pan across here, first off, there's a hole right there at x equals 2. And that's because if you try to plug in x equals 2 into the denominator, you get 0 over 0, so it's undefined at that point. But then anywhere else close to y equals x equals 2, the y values are getting really, really close to negative 0.25 or negative 1/4. So that's just confirming what we found algebraically. I wanted to show you what the graph looked like. All right. Okay, and now in problem 6, we're looking at the cost of printing flyers at Office Depot. And to create this table, I actually went to Office Depot's website and looked up the cost of printing flyers. So these are actual values from 2019. And so if you look at this, it says that the cost of producing 0 to 99 flyers is 42 cents, but then the cost of producing between 100 and 499 flyers is only 33 cents per flyer. And then if you produce between 500 and 999, you get another quantity discount, and you only pay 28 cents per flyer. And then finally, anytime you produce more than 1,000 flyers, I guess they're going to charge you 24 cents per flyer. And so this is the graph of that table, well, of this information here. You can see it's a piecewise defined function with jumps at the values 100, 500, and 1,000. And it says, the first question asks, does the limit as x approaches 100 exist? Explain your reasoning. And so that was this value right here. And it does not look like that that limit exists, and that's because there's a jump discontinuity. Because at one point you're paying 42 cents per flyer, and then at 100 you switch to paying 33 cents per flyer. So it's the left-hand limit, I would say, is the limit as x goes to 100 of 0.42x, whereas the right-hand limit is the limit of 0.33x as x approaches 100. So let's see here. Does this limit exist? Explain your reasoning. No, it does not. And my reasoning is going to be better explained using the math terminology. So what is the limit as x approaches 100 from the left of c? Well, let me just write that down in green. That's the limit as x approaches 100 from the left of, let's see here, I guess that is 0.42x is what c is defined at that value. Okay, so that would be, if I were just to plug in 100, that'd be, looks like $42, or 42 times 100. Yeah, so that's 42. And then the limit as x approaches 100 from the right, well, that would be the limit as x approaches 100 from the right of 0.33x, so that's $33. Okay, so you can see that these limits are different. Let's see here. Okay, so then you have to make 1,000 photocopies. Would it be better to make 999 or 1,000? Explain your reasoning. Well, it's pretty clear from this picture that you're better off making 1,000 copies because the limit from the right at 1,000 is lower than the limit from the left. So you are better off making 1,000 copies because if we're going to use the math terminology, the limit as x approaches 1,000 from the right of c is equal to the limit as x approaches 1,000 from the right of, what was the function defined to be there? 0.24x. And so that will be 1,000 times, 0.24 times 1,000. So that's, I think, $244. $240. Whereas the limit as x approaches 1,000 from the left of c is the limit as x approaches 1,000 of 0.28x, which would be $280. So by making one extra copy or a flyer, you save yourself about $40. Okay, problem 7 is kind of a review problem from things we've been talking about in the last week or so. It says the function f of x, x squared minus 1 over x plus 1 is a, and you guys should all be screaming this right now, it is a rational function because it's a ratio of polynomials. And so where is it discontinuous? It is discontinuous where the denominator equals 0. So it's discontinuous where x plus 1 equals 0, or equivalently where x equals negative 1. Okay. Problem 8 says the function f of x is x cubed plus 2x plus 1 is a, again you should be screaming, it's a polynomial function. And so where is it discontinuous? And you should say nowhere, because polynomials are continuous everywhere, And rational functions are continuous everywhere except for where the denominator is equal to 0. Okay, so those were just review questions. Hopefully you've gotten that theory down. And if you have, then it'll make your life a lot easier going forward. Okay, graph each of the functions, decide where they are discontinuous. Okay, so f of x equals 1 over x. And now to graph this, I recommend you just make a quick table if you don't know what the graph looks like already. So you can plug in x and y, and again, pick nice values. If you plug in -3, -2, -1, 0, 1, 2, and 3, you should get a pretty good idea of what this function looks like. So we plug in -3, you're going to get -1/3. -2 will be -1/2. -1, you get -1. 0, you get 1 over 0, that's undefined. Undefined, that's a vertical asymptote, so that tells me that this graph is going to have a vertical asymptote at x equals 0. And then what else? Well, if you plug in 1, you'll get 1. If you plug in 2, you'll get 1/2. And if you plug in 3, you'll get 1/3. Okay, so now we have a pretty good idea of what this function looks like. We know that at -3, it's -1/3. And then at -2, it's -1/2, which would be right about there. And then -1. I could also plug in some values closer to y equals x to see what's going on. If I plug in -1/2, I get +2. Oh wait, did this completely wrong. I'm ignoring the signs here. So I have -1/3 would be there, -1/2 would be there, -1 would be there, -2. I said if I plug in -1/2, I said I'd get -2, and if I plug in -1/3, I'll get -3. So you should be able to see this graph is looking something like this. So you have a horizontal asymptote of y equals 0 as x goes to -infinity. We have a vertical asymptote that goes to -infinity as x approaches 0 from the left. On the flip side, I can plot these points that we've already marked, and then again, if I plug in 1/2, I'm going to get 2, and if I plug in 1/3, I'm going to get 3, and if I plug in 1/4, I'm going to get 4. So the function looks something like this. So we have a vertical asymptote at x equals 0, and let me just write down some of these behaviors. So the limit as x approaches 0 from the left of f of x is -infinity. The limit as x approaches 0 from the right of f of x is +infinity, because as I'm getting closer and closer and closer to 0 from the right, the y values are taking off towards +infinity. And then I can also say a few more things using limits. I can say that the limit as x approaches -infinity of f of x is 0, and that's because the y values are getting closer and closer and closer to 0 as x approaches -infinity. And I can also say that the limit as x approaches infinity of f of x is 0, because as x gets really large, the y values are getting closer and closer and closer to y equals 0. Okay, so that's f of x. Now g of x is what type of function? Hopefully you're all screaming that this is a polynomial, which means it will be continuous everywhere. Oh wait, I was supposed to say where this was discontinuous. Well, this is a rational function, so it's only discontinuous where the denominator is 0. So it's discontinuous at x equals 0. That was the vertical asymptote. Okay. Now for g of x is x squared minus 3, hopefully you know what x squared looks like. So you can either make a table if you need to plot points, or you can remember that x squared looks like something like this. It's a parabola that goes through 0, 0, and -1, 1, and 1, 1, and 2, 4, and -2, 4, and so on. And this is just x squared minus 3. So we take that shape and we shift it down. So this is, what I'm plotting here is not the function that I want to plot. This is just y equals x squared. But now y equals x squared minus 3 is the same plot, just shifted down 3 units. So in red I'll plot the actual curve that we want. Let's see here. Something like that. And so this is g of x equals x squared minus 3. It's a polynomial, so it's continuous everywhere. Okay, so again, we took the purple curve, which was y equals x squared, we shifted it down 3 units, 1, 2, 3, at every y value. and that's how you get the red curve. Okay, now the last curve is h of x equals 1 over x squared minus 1. And so again, you can create a table and plot some points, or you can try to decide where the horizontal and vertical asymptotes are, and that may help too. So I'm going to start off by saying, okay, when is the denominator equal to 0? That's when x squared equals 1, so that's either x equals plus or minus 1. So those are my vertical asymptotes. Okay, now I'm going to make a table and find some points. So we have x and y. So now if I plug in negative 2, let's say, what happens? I get 1/3. If I plug in negative 1, I get, oh, that would be a horizontal asymptote. If I plug in negative 3, what happens? Negative 3, I get 1/8. Okay, so negative 2, I'm at positive 1/3. And then at negative 3, I'm at 1/8. And if I keep plotting larger values, I'm going to get 1 over that large value squared minus 1. And so that's going to get closer and closer and closer to 0. So I think I have something that looks like this. And the limit as x approaches negative 1 from the left is positive infinity. And then if I plug in, let's see, if I plug in 0, I get negative 1, so I know that's a point on my curve. And then if I plug in, let's say, negative 1/2, then I'm going to get 1 over 1/4 minus 4/4, so that's negative 4/3. Okay, so I think I did this in class actually last week, so I'm going to go through it pretty quickly. I think the graph looks something like that. This should be a review of something that we did last week. And then finally, if I plug in points over here, I'm going to get the mirror image of what I got over there. So if I plug in 2, I'm going to get 1/3. If I plug in 3, I'm going to get 1/8. If I plug in 4, I'm going to get 1/15, and so on. So you can see that this graph looks something like this. Okay, so that's what the graph looks like. And again, this is only discontinuous where the denominator equals 0, and so it's discontinuous at x equals plus or minus 1. And now I just wanted to show you on Desmos what the function we just graphed looks like, just to confirm that just the few points that we plotted was enough to give us a really good idea of what was going on. So there is y equals 1 over x squared minus 1, and you can confirm that x equals negative 1 is one of the vertical asymptotes, and then x equals positive 1 should be the other vertical asymptote. You can see that's pretty much exactly what we had graphed just by plotting a few points. Okay, so that's all I had for today's activity. Hopefully this is okay and that most of everything has made sense. We'll talk again on Thursday about this stuff, but I didn't want to let Hurricane Dorian get us down. So this way at least all of you have a chance to work through the packet on your own and then check your answers against mine. Okay, have a great day. Bye.